MSc and PhD in Power Systems from University of Canterbury, New Zealand. He specializes in developing innovative business using dynamic learning activities, especially simulators, for knowledge capture and transfer. His company has trained system operators and trainers to operate the world's most challenging power systems. The INCSYS Academy, with its digital virtual instructor, has assisted over 300 veterans to start or advance their system operator careers with 90 different companies. He played a key role in the startup and growth of ESCA, now GE Grid, INCSYS, and IEEE Smart Village Entrepreneurs in India and Africa. He is an IEEE Live Fellow and a member of National Academy of Engineers. Welcome, Robin, to our ESIC seminar today. Dr. Robin Podmore will be talking to us about accelerating power application development in today's seminar. So back to you, Robin.
It's wonderful to be here, Amnika, and there's so much happening in the world today that I just want to thank all of you who are dedicating your careers in the power industry. It's been a wonderful journey for myself and my family. And let me share my screen and desktop window, screen one. Let's see. Are you seeing my PowerPoint?
Yeah, we are actually seeing your Teams window.
You're not seeing my PowerPoint in view mode?
No.
All right, let me stop that. I must have shared the wrong one. Okay, open share tray, screen share desktop window. How about screen one? How about this? Can you look now?
No, Robin, we are seeing your Teams meetings window instead of the PowerPoint.
How about now?
So now we are seeing your slide, your Microsoft PowerPoint, but the slides are basically not in view mode. I can basically see the slides.
No, we're getting there. Perfect. All right.
Okay, great.
That's great. All right, so let's go to slideshow from the beginning. And here we go. All right. So the title today is Accelerating Power Control Application Development. And I'm presenting primarily as the founder and president of INCSYS, Incremental Systems, but I also have the honor of being a co-founder of IEEE Smart Village and the founder and president of a Rotary E-Club of Smart Village. So I'll be bringing some mention of those activities into the presentation. Obviously, let's just keep all the wonderful people in the Ukraine in our thoughts and prayers as we go forward. One of my first positions in the US was a postdoc fellow in Saskatoon, Canada, and that's where we got to know the wonderful people of Ukraine. They're dedicated, their hard work. It turns out that the rich black soil of Saskatchewan is very much what they have in Ukraine. And we had the pleasure of just experiencing their way of life, their dedication, their joy. And so let's just keep hoping and praying that everything turns out all okay. So, and I just want to, I spent some time, I actually took a photograph of all the participants that were at the presentation by Peter a week ago, and I know that on the call we have people from across the globe, people from Nepal, people from India, China, and Sri Lanka, and of course some that are homegrown in Washington State. And I just say thank you all for coming together at Washington State. I know the weather is a big shift for some of you, but you've got the warmth of a family there that truly has been established by wonderful people like Anamika, like Professor Bose, and like Noel Schultz. So you're in a wonderful community, and I believe those for Stella and me going to Saskatchewan from New Zealand was just a total change. But the things you'll build there are friendships that will sustain you for your career. And I want to make that out is that once you join IEEE, and if you're not a member, please join, you've come into this amazing family of people that will help you as you go forward throughout the world. So I really want to get two key messages across today. I had a dear friend, David Ivanga, said, Robin, what's the big idea? So the big idea for this presentation is we have a lot of experience accelerating. My company has experience at accelerating the experience of power system operators with a simulator and what I call a virtual instructor. And what I want to do is plant the seed that we would love to work with every one of you at all levels in your organization, okay? On how can we accelerate the process of power system researchers with a power system application framework. So for the last, since 1990, we got serious about how to use our simulator to work and train system operators. And this quote from Mike Anderson, supervisor of transmission and real-time operations at American Electric Power. Mike says, our trained veterans that they've hired have helped us close the gap by 2 to 4 years before they can then take those candidates and put them on the desk with sole responsibility. Not only are they NERC certified, but they've been tested that they can do all the critical reliability related tasks. And so they have been very, very pleased with the program. So I want to make sure that we all recognize that PowerSimulator, which I'll be talking about, is a product built by a combination of INCSys and PowerData, and it uses the EPRI Operator Training Simulator engine. So INCSys and PowerData, there's 12 of us in total, and there you are, Leroy, looking good. So so this was our last physical get together at a user group, and I just want to say thank you to all of our customers around the world and acknowledge that together we've built this simulator, which is very, very good at simulating and training system operators. So our goal is to help the operators run the systems, obviously safely, reliably, economically, and adapt to all that uncertainty and variability in the generation demand, the weather, the threats, the technology, regulations, markets, competition, and customers. So we've managed to do that in a really good way. I'd like to, at least as the process of in training system operators, we've had to really understand some very key learning theories. And one that we really like is the idea of the difference between implicit and explicit knowledge. We've created a hypothetical system called Cascadia. This is totally hypothetical, but it's layered on the geography that you all know really, really well. There we are, Alan Pullman. And, you know, we're about 300 miles across state, and it's a 500 kV loop and 230 underlying. It was inspired by the system in California where we had the blackout of 2011. Basically, there's a 500 kV loop that went from San Onofre across to Palo Verde and back to San Francisco, and then a lot of 230 on the coast. So we can actually simulate the phenomena of that blackout. So this model is very, very useful to understand what's happening in our industry. Historically, we had apprenticeships where Joe, the senior system operator, would spend time with, say, Bill, the operator in training, and Joe would share his tacit knowledge. Your tacit knowledge is your intuition, your gut feeling, and it's not written down, okay? So that is, but there's huge amounts of tacit knowledge. What we have to do is we have to take that tacit knowledge and make it external and get explicit. You can measure the degree of content and sophistication of any training program by asking simply one question: how many scenarios do you have documented? Those scenarios and their solutions are taking the knowledge of an expert and putting it in a very explicit form. So you've got a base case with a certain load flow condition, you've got a certain event file, and then you've got the documentation of how the different experts actually run the system. There's a catch-22 that the more advanced the senior operator gets, the more intuition they have, and the harder they have a time to actually express their knowledge in a really explicit way. But you can actually take an operator that's been retired for, say, 3 or 4 years and provide them with a simulator, and they get back into the moment like you wouldn't believe. So the idea is to document what they're doing, interview them on their thought process, and get it all explicit so you can replicate it. Now, if all this knowledge is on all the specific systems of the customers throughout the US, then we can't share it. Those models are called CEII, Critical Electric Infrastructure Information. So you have to take that knowledge and put it into a platform that you can share. And we do that with the Cascadia system. And then the operators, you as students would train with that system, and you would build up your own intuition. So I'm inviting you to get engaged with our whole training program. We can help you even get Nerc certified. We can bring you to a meeting where you're actually doing a shared session with real operators, and you can be job shadowing them, and then you can be running the system. So here's the idea. This is the state of Washington. We take what we observe from all our different customers throughout the US and around the world, and we put them onto the Cascadia system. There was a very severe transformer outage, I think it was 2014, in West Wing, right next to Palo Verde. 4 transformer banks blew up and got on fire. We've dramatized, okay, in the northeast and the southwest part of our system. And of course, we're not pointing the finger at any individual operators, but we learned a lot from that scenario, and then we brought it to life. So one of the things I've also had the amazing joy and experience is training people around the world. We had multiple sessions with Kenya Power and Light running on their system. Through the championship of IEEE Smart Village, we sponsored a number of entrepreneurs. This is a system, Ifeanyi Arajaka, the main recognized mini grid supplier in Nigeria. And then we've also been involved with the different power pools around the world. So this is a meeting of all the operators from the 13 countries in the Southern African power pool with Saifa Rahman, with IEEE, Bai Blyden, and some people from EPRI. Bai's great-grandfather was very renowned for his work on the original Pan-Africa movement. And so there was actually a little RFP came out from NREL called the let's see, American Made something. Sorry. So yeah, American Made Challenge. So I put this slide together to capture the fact that, look, we could really help a lot more people of minorities in Africa, the Middle East, Asia, and Latin America. Black and brown men and women design, build, operate the mini grids and the national grids, but you don't see too many minorities in the utility business in the US. So the idea is NREL wanted to get them all engaged. So we wrote a little proposal that said, let's take our Nerc certification process. Here are some of the graduates of our process. We started a program called Power for Vets back in 2010, 2012. We're very proud. We've placed over 300 veterans with 100 different companies, and we have a better than 98% success rate at Nerc certification. And these are some of the, now the Nerc test, I want you all to seriously think about it. Basically, it's a 125 question test. It takes you 3 hours at a testing center. And when you get certified, you have a license to run the US grid. Obviously, you've got to go through more training, but it's an extremely great certification to have. Why am I suggesting that? Well, right now, I believe we all work in these different silos, all right? We've got the system operators. These are the people that are really savvy, but sometimes they grew up with as a lineman, as a substation operator, and power plant operator, and they have an extreme amount of field experience. They know how to work the long shifts. They're very good at the discipline and the safety procedures. Otherwise, you know, if they make a mistake, we have blackouts, we have lives at stake. But they're not necessarily into doing a lot of math. So the point is we have to take all the concepts and make them really straightforward. And basically, you don't want an operator doing calculations on the fly. They've got to really have trained and anticipated those things ahead of time. Then we have our operations engineers that are very familiar with the power flow, the stability, the system protection. But right now, our tools like the power flow and stability are not intuitive for system operators to use. So that's where we need better simulators. We have the developers. I mean, some of you probably know what transient saliency is, okay? You know, it's the fact that a generator can be a round rotor, or if it's a hydro one, you know, it's very asymmetric. So the point is, you've gone through all the books by Prabhakunda and so on, and you understand in great detail how to model a power system. And then we've got our friends that are into the cyber coding that understand object-oriented in Java and so on. So the point is, what I'm saying is, please be careful that you don't take one of these areas and become more and more specialized over your career to the point where you know everything about a very little, all right? Please start branching out and also building your expertise across the different disciplines, all right? And I'm encourage you, just because you're starting out, say in your PhD, don't put all your entrepreneurial talent on hold. Look for a way to start a business, okay? Maybe back in your home country and start volunteering. I didn't start volunteering with IEEE until about 10 years ago. And I'm saying, if you start volunteering now, not only will you'll get a lot more back compared to what you give. There's another principle. The amount of knowledge in this around the Zoom session right now is, hundreds of times of more knowledge than I have in my head. So again, I'm to be able to present, but the one rule of training is that the audience knows a lot more than the actual instructor. So we have to create tools to bring out that knowledge, and that's the beautiful thing. Now, I'm going to come up with a couple of definitions. An application framework is a library that provides the structure to support development applications for an environment. So we're proposing a structure to build power applications, and it provides a skeleton. And then in a software sandbox, we want an environment where we can play with it and not crash the real system, okay? The real system obviously has to be running 24/7, and we want to replicate the functionality of that system. So here's how we would run a drill before we had COVID. We would get all the folks from California, you know all these names, they would get together in a huge conference center, and we would have this little kit. It became named the BRIC, Bulk Reliability in a Compact Kit. And that server would actually be there in the corner, providing a simulation of the entire California system. Since that time, most of our customers have obviously gone to running on the cloud, and they stay either in their backup control center or in their home office, and they're able to participate in the drills. So they are actually using a replica of their own substations. These diagrams look exactly like the substations they have in the real world with the right names. And they're there, doing their black start. And then at a certain point, they will actually synchronize. Literally, everyone will stand up and cheer when you synchronize two major islands together, because that is a huge step forward. And so you get a lot of teamwork there. But more recently, we have gone to where people are running on the cloud, and you can literally open a breaker. You can be you could be in Western Washington. You open a breaker, and you, as an instructor, you fault, say, a 500 kV line, and everyone throughout the whole interconnection will see that happen, like it was happening in real world within a couple of seconds. So I will cover a little bit about the types of models we use. A lot of you use PSLF, PSAF, and you use what we call a planning model. And now we've turned that into what we call a reliability model. Operators need to see things within substations. So if we see a transformer connecting two buses, we'll put that in a single substation, and then we put a single breaker at the end of every device. So serial devices will have 2 breakers at the end. Devices to ground will just have a single breaker. So here's a generator with a single breaker. Here's a transformer with 2 breakers. And then these breakers are actually artificially numbered. It's not the real breaker that the operator likes to see, but they get used to this. Within about 15 minutes, they're actually running the system, seeing voltages and currents and frequencies like they would in the real world. But that's just the first, and these diagrams are all automatically laid out. What they, of course, really want is the actual detailed breakers and switches of their exact system. And the industry has made enormous progress. Right now, you can exchange these the models with this level of detail, as well as the diagrams, in a format called SIM, Common Information Model, XML, Extended Markup Language. So over decades, we now have these SIM XML models available pretty much for the major systems throughout the world. And that obviously is huge, because we can come along and offer a simulator to a customer, and they have to spend a lot more work building their displays and their models. So together with Power Data, we have pretty much modeled all of the continental United States for various times with the reliability models. And recently we modeled all of RC West with the switching model. We've been running with California for many years. We did do some work with Alberta, and we've been having a switching model for ISO New England. But now with the SimXML, it's a very straightforward process to get those models available. Now, how does that help you as a student? Well, in some cases, you can actually have a non-disclosure assigned through and protect all that information. Or if you work with us on an internship basis, we can actually get the right clearances where you can have access to those actual models under non-disclosure. But you're realizing that this is extremely sensitive information. It's, you know, we need people that are absolutely can be trusted. But I know that you've, to me, if you're willing to move to Pullman from some nice sunny place, you're very committed to the industry. So I congratulate every one of you for making that commitment. So here's an example of the kind of model. Sometimes it frustrates me, okay, to see you all writing papers on the IEEE under 118 bus system, because that system was quite old when I was a very young man. It's from about the 1940s, I believe. So we want to get you models that are a lot more realistic, that have actual breakers and switches. So this is the kind of dimensions. This is actual, the RC, the full Western United States model has close to 100,000 disconnects, 50,000 breakers, and 150,000 nodes. And with today's computers, handling this is just not an issue at all. I can set, you know, even on my own desktop, I can set up arrays for millions of nodes. Now, but clearly we have to have much smaller models as well. We are seeing the phenomenon of inverter-based resources having a cascading effect. One gas turbine will trip offline, and the wind farms and solar farms in a 200-mile radius will see that voltage dip, and they will also decide to trip off. And Nerc has been saying we've got to run the EMTP studies where we actually simulate the waveform. And what that requires is we come up with dramatically reduced model sizes. So last year when we had the last 2 years when we had the COVID, I spent a lot of time about how can we really create models that are much more reduced in size. So here's a model that was created for the Western United States systems, where what you're seeing here, the numbers, everything is converted to a 230 kV basis. And this is the distance in miles for that particular circuit. Let's see. Yes, that's, So the impedance of a 500 kV line typically is about 0.0002, and the impedance of a 230 is about 6 times that. So basically what we do is we convert everything to a standard distance, and with a 41 bus 56 line model, I can simulate pretty accurately the trip of the Pacific. Okay, so we've got two DC lines in this one. We've got the Pacific one, typically taking about, let's see, 1,000 megawatts, and then the Intermountain one, about 2,500. And if we trip this line, this is the predicted flow from the electrical distance diagram in blue versus the full detailed power simulator model. And so it's pretty close, okay? So the idea is to come up with a reduced equivalence so that we can do the very detailed simulations going forward. So look, let's, how are we doing? Now, we also need to have a single, we tend to have two different worlds, the transmission systems and the distribution systems. The transmission systems chop everything off at the distribution breaker or even higher. The distribution systems assume an infinite bus at the breaker that controls voltage and frequency, can simulate a radial system. As you all know, that's totally changing. We're looking at significant generation down the feeder, a shopping mall at 11 kV with 5 megawatts on its roof. And so we have to come up with a single model that can find the best simulations of transmission and distribution together. Now, in transmission, the faults are typically, when you have a fault on any element, there's a zone of protection that you have to clear and open the breakers to isolate that faulted device. In a distribution system, we're used to everything running radially. So in a distribution system, you're always looking at the next device upstream on the feeder. So simulating faults is very different between the two systems. But everything else can be done on a more common basis. We have the computational power right now to really simulate the three-phase flows on the transmission system if we can boil them down, not having to model, say, the entire interconnection. So, you know, you've all used Google Maps, and basically on Google Maps, you can get a detailed route from a given house on the East Coast to a given address on the West Coast. Why can't we do the same for our grid and track how the power flows run from any generation source to any load? Well, here's the problem with that. Let's say we're about 1,000 gigawatts right now, you know, divided across the Western, the Texas, the Quebec and Eastern interconnection. Assume the average customer is 5 kilowatts, then you division, and we'd have about 200 million load buses. And we don't want to be simulating the whole system down to the customer transformer of everybody. So what we have to do is we've got to come up with equivalencing techniques that really keep the equivalent effect of a huge interconnection and let us zoom in and see the impact of individual distribution feeders. There was an event a couple of years ago where there was a gas turbine was opening and closing its valve in Florida every 4 seconds, and that stimulated a 100 megawatt oscillation across the entire interconnection from New England down to Florida. It was like a seesaw effect, okay? And so we need to simulate that. We need to do detailed simulations of all of the different phenomena that can occur and not just do it after the fact. Our track record has been, we'll have something like subsynchronous resonance that will destroy the Mojave generator shafts, and we do all the simulation after the fact. We have to get ahead of the game. We have to be simulating anything that gives you a oscillatory phenomena in advance and then recommend to the suppliers how they need to adapt their systems to deal with those phenomena. So we developed the Goldilocks principle, all right? We cannot model the entire system down to the customer transformer or even the distribution feeder. So the Goldilocks principle is the power system should be modeled to the extent required to meet the training and the study objectives. So the vision is you'll be able to, almost like on Google Earth, you'll be able to build a scope of a model where you want to say, look, I need to have all the thing about the interconnection is it provides governing response, it provides voltage response. So the idea is to be able to build much smaller models where we keep the overall governing and frequency response and voltage response out of that interconnection. And please just realize whenever you put an infinite bus system in any interconnection, you totally destroy the ability of that interconnection to model frequency response and model VAR response. We have this of sticking these big infinite generators in a model, and we're just totally destroying the response of that system. Please, we can't do that. We have to model all the inertia and all the megavar response. Now, we've had some great, I've had the privilege to work with the ADMS project with Northwest Labs, with Alexander Anderson, and it's been a great team where we've built a synthetic 9500 node distribution system. So we're seeing some very good synthetic models available right now. And we're able to, there's a new neighborhood here with 100% penetration of solar panels, as well as battery storage. There's an old town that has an old, let's see, steam plant, a combined power system. And I do want to make a, I think Alexander's on the call. Alexander, I think he published his first IEEE paper at 18 years old, and he got his PhD when he was 23. So congratulations, Alex. And the whole idea is we enjoyed working together. And the whole idea is through extensive simulation, you can really, really accelerate your work. So one of the things that you may all be familiar with is the levels of technology through ARPA-E and DARPA use this guide. Now, our power data team is really working at TRL 9 all the time. Our nightmare is we've staged a drill and we have 100 operators showing up and the simulator's not working, okay? The team at Power Data rehearse, practice, and get really good at making sure that when we have that level of operator engaged, that if there is a blackout, we can understand it, we can back up, we can go forward, and then even right then or even that evening we're explaining. What we find is whenever there is a blackout, there's a really good operating lesson. It's not the technology, it's somebody actually push the system beyond a voltage or stability limit. But you are all typically working all the way from level 1 up and 5 and 6. You're doing demonstrations in a relevant environment. Our goal is to get you off of that 118 bus case and get you onto large scale practical models so that really you're up on this level 7 for sure. Now, there was a very interesting comparison. Was that how are we doing? We're still good. So John Alex said, look, Department of Defense systems are huge and hard to manage. And they pointed out the difference in a weapon system is not just a few scientific advances, but the effect of hundreds of little advances that are not so significant. And I give credit to our power data team. The 2016 user group, they've been listening to every one of our trainers and really continuing to make changes to the simulator. Things like adding roles and responsibilities, push a button and all the displays come up to reflect your role as a transmission operator for a certain part of the interconnection. So the idea, if you're guided by the users, but also the people who do the training, then we can figure out our agenda. So what we can do is we can help you. We can take your ideas, we can bring them into a training scenario, and we can have real system operators actually vet those ideas and give feedback of how well does it work. And I make an appeal, please show the respect to the real system operators. Don't be out building some optimization without spending the time to figure out how does a real system operator handle that situation in a real world scenario. A lot of the artificial intelligence is not suited to all the deep learning theories. It's simply coding up the if then else statements which a system operator would use. There's a low hanging fruit there. So what we're proposing is a power simulator application framework. This is the actual power simulator product here. It has its own real-time database and message bus, and these are all the level 9 application programs that we have. Now, it takes a lot of experience to be able to be writing this code with the Java level. You need to understand Java, you need to understand power systems, you need to understand object-oriented. That is not my strength. What my strength is running things like Visual Basic or Python and getting an application to work to make sure that it solves correctly and is and handles the solutions and comes up with a zero mismatch solution and comes up with all the different types of simulations all the time. Now, there's been a couple of challenges to really be a production programmer. One is the MRIDs. These are the master resource identifiers. You need to be able to handle these very long arbitrary identifiers. You need to be able to handle system topology and breakers and switches. And then, of course, you need to be able to understand all the power flow equations and so on. But recently, what I've been doing is really bringing together a piece of code that I've written over the last 5 decades and making it run in this environment and getting ready to share it. So we basically have all these applications running in a, I like to use Visual Basic, but we can translate that to Python, which is much more commonly used. So what I'm encouraging is you to actually sign up, get involved, and start using this toolkit for some of your research. There are some new technologies like graph databases that can be super blazingly fast, and that lets us do what I call a sandbox and a prototype very, very quickly. There is a simple LINKNET storage mechanism, which was actually first published in 1971, believe it or not. And this is a very, very simple, elegant way of storing a network. We basically take all the branches in a network, number branch 1 with the ends 1 and 2, and form linked lists of the ends that are connected to each node. And then for each end, we have a pointer to the far end. So this makes programming very, very straightforward. This is how you add something to the top of the list. And this storage structure is used for everything. It's used for topology processor. It's used for the admittance matrix. It's used, so we've got one very simple structure that can pretty much store everything. For those who are in Python code, there's almost been a fear in our business about dealing with system topology. It's crazy, that we still have planning programs that represent everything as an electrical bus. When you go to an operator and you show them the bus numbers out of PSAF, they say, what's a bus? They're used to a bus to them is a bus bar. It's not the fact that all this stuff is in a power system engineer's language. We say, well, this is a bus because everything is operating at the same voltage. But those programs don't deal with the fact, what if I split this? What if I open all these breakers? All of a sudden, I've got two buses. So those programs are totally inflexible. It's a nightmare to update those programs to the things that can happen on the real system. We got to get away from that. This was excusable back in the 40s, okay, but not anymore. Now, finally, we have the vendors of planning programs supporting breakers and switches, but it can be a nightmare to actually model that. So we've got this huge gap between what an operator looks at. But let's back on up to figure out what are the topology. So we have the topology bus is that everything is at the same voltage. So really, we simply build a spanning tree. There's no need to be fearful of topology processing. Literally, that's the code there, okay, to build a spanning tree to create an electrical bus. It's about a page of code. So please start working with real breakers and switches so that your software can be understandable by real operators. My setup is I've got a really nice Microsoft Studio, and I'm able to actually call up the substation displays and then browse the code and trap it so that I can see all those voltages as on the actual substation. So literally, right before Thanksgiving, things are kind of quiet during the Thanksgiving. I got back in serious coding, and I've been building prototype code on a 150,000 node model of the Western United States interconnection. The software we're willing to share. It will be under a license, but you'll get access to it through the Academy. So as we've gone to the Common Information Model, they've come up with these master resource identifiers. Look at this, 32 characters of hexadecimal. And these things drive, a power system engineer nuts, but there's a simple routine where you can just convert that to an offset, okay? Convert that to an offset from one to a million, and now we're dealing with numbers that we all love. So this is the number of lines of Python code to do these different applications. It's not that great. The whole power flow is 500 lines. The decoupled, this is the linear power flow. The decoupled is about 500. The bus flows is 460. Here's your factorization forward and back. We've got all the turbine dynamics. So I'm looking for people that want to jump on in, start taking this code, and build more applications. So we're going to finish a little early, but that's good. There'll be time for questions. So we're looking for partners that can build a universal T&D power flow that will solve three-phase unbalanced as well as three-phase balance altogether, a fault location and system restoration, so that when you have to roll, you've got a major fault on a distribution circuit, and how do you roll the circuits over to be fed by what's available. The dynamic model reduction is a very low-hanging fruit. I honestly believe we can be coming up with models that are accurate at about 1/10 the size of what they are now. We need a substation sentinel. We need to have something that literally runs every millisecond and detects malicious actions. The amount of damage a sophisticated attacker can have on every major transformer, every major generator is outright scary, all right? We need to have that substation sentinel opening right there. All this software can be distributed in the processes. So I'm looking forward to just start on with a collaboration. The benefits, you will get experience with large-scale real power system models. I honestly believe you'll get your PhD done faster. We'll help you publish papers of a high quality. You'll work with understandable, powerful source code. You'll participate in drills with real operators. You will have an option to get Nerc certified. On a typical DuPont shift, you may work 14 days in the month, 12-hour days, and you get the rest of the time off to basically pursue another business. The nice thing about a system operator, when you do your shift turnover, you can pretty much leave your job behind, okay? And it's not like you've got your, it's very unusual where you've got a lot of homework. I encourage you to check out IEEE Smart Village. It's a wonderful group where you'll meet a lot of wonderful people. And what's happening is, it turns out that the architecture to feed all the wealthy people in California when there's an outage is the same architecture as to light up a lot of villages in Africa. We're getting the grid forming, grid following inverters, and you know, a PV panel is a PV panel, and so there's a lot of technology sharing between looking at what we're doing in Africa versus the US. And I can get you access to a 1 megawatt solar system that you can do all your testing on in Africa that you can't get to play with in the US due to all the other concerns. And then, yes, we can work to coach you so that you can start a business in parallel with your degree, with your colleagues back in your home country. Or anywhere, okay? So the point is, we have this huge, you've joined this huge community right now. And again, I really want to thank Professor Andrew Bose for being such a great colleague. Professor Noel Schultz was the president of Power and Energy Society when we started the IEEE Smart Village. And so really, you're part of a wonderful community. And there's a lot of us that just really would like to give back. And every time we give, we just get so much more and learn so much more from everything that you're doing. So let's open it up for questions. Yeah.
Thank you, Robin. This was an excellent talk on different topics with what's changing and what's required in the power industry. Really appreciate you spending time with us. We have one question here in the chat window. Let's start from there. So the question is, what method will you suggest for dynamic model reduction?
Basically, what we do is we use the concept of an electrical distance, and we cut out all the underlying lower voltage circuits that are not in. If you have underlying lower voltage circuits with other higher voltage circuits in parallel, you can just delete them from the model. But if, for example, those circuits are there by themselves, like in the Northwest, we've got some circuits going all the way from Montana down into not into Wyoming, into Utah. So the idea is to use a lot of judgment where just keep those underlying voltages when they are really needed, because and so as a result of drawing out, we have a way to draw out the Western interconnection with a directed graph and really understand where you need to keep the critical circuits. So it's a combination of using electrical distance to understand circuit compared to everything that is all around it. Okay. If you look at the Western interconnection, then we would the Eastern interconnection, we would obviously keep the 500, keep the 345, keep the 230. And then like in TVA, it's a case where you've got a lot of 500 with a lot of underlying 161. So you're really going through your objective and saying, what circuits do I need to keep in order to have a good model? And then the other thing we've found is that you can move generators and load around from one circuit to from one node to another and still get very good performance. You can preserve the megawatt characteristics just by moving that generator from one to another and keep its megawatt D curve. So that's the, you know, I did all this stuff on coherency a long time ago, but this is an even simpler method.
Great. So a follow-up question is, does the platform support islanded operation of a part of the grid? And also grid forming inverters are implemented. So probably more from the distribution side, this question.
Yeah, I've been talking with Alexander about coming up with, islanding is in our blood for, when we do a black start, we can have as many as 40 islands on the WEC interconnection, okay? Because everyone is just going, but we have to do, It's crazy right now that a municipal utility may sit around for a day and a half for the investor-owned utility to run them a hotline, okay? And so we have to do the islanding where you can use whatever resource is available, because we're seeing major outages and the storm goes through and the sun is shining and the wind is blowing. We need to take advantage of those distributed resources. National actually has a full-blown project on how to restore the system from distributed renewables. So we do have to build a transient stability based software for the distribution systems that can have all of those. So well, and you're doing that yourself, okay? You've been running the restoration. So yes, that's the next generation, is to really get off of the specialized code for distribution modeling and truly make it network based as well as transient stability based. And getting those models for the grid forming inverters is huge.
Mm-hmm.
As well as the fact that those panels can provide a regulating resource. Okay, so you can actually have your all your PV devices can even be dynamic voltage sources even when the sun's not shining. Okay, because they've been built to handle, the inverters are built to handle 100 megawatt. They're limited by MVA, so you can produce 100 megawatts and 0 megavars, but during that time you can produce 100 megavars and you can and 0 megawatts. So we really have to start thinking from a very strategic viewpoint for distribution.
Yeah, makes sense. Let's see. I'll also open up for audience they can unmute and ask questions as well. So I have a question from Steve here. Given that some of the ADMS and EMS vendors offer a training simulator to the electric industry as a part of their respective platforms, how does the Power Dispatch / System Operator Manager justify the use and related work associated with the implementation of the INC-SYS Power Simulator? How do you see the derivative works from the cooperative efforts be rapidly integrated into the Power Simulator?
Yeah, we've seen our customers in California have really pushed the idea that it's okay to have more than one simulator. In planning, we accept the fact that having more than one simulator is good. In the past, people have really been concerned about all the additional workload. So the idea is we're offering a simulator that not only can model your as-built system, it can model your systems in the future. And we're actually finding that people can build their scenarios much faster with PowerSimulator because it's much easier to use. And then they take all those scenarios and they put them on their real replica system. So we're finding ways to be very, very complementary with whatever simulator technology they have in place. Because yes, there are cases where you really want to have that full replica where the operator is really sitting there and is really running their own system with the exact look and feel and the exact displays. But there's plenty of room for both compared to the needs that are out there now.
Great. So yeah, I'll open up for questions from audience. If you have any, just raise your hand or you can unmute yourself and ask. Meanwhile, I'll ask a question, Robin. So as you have been working on the simulator platforms and modeling the power grid, right? What kind of shift you are seeing as the integration of new technologies now happening at the distribution level? How is the overall modeling paradigm for the electric industry is changing as we are seeing more grid edge resources being integrated?
Well, we're seeing these inverter-based devices just not behaving the way we thought. And so we're seeing Nerc say things like, we should really run EMTP studies. Okay, well, running EMTP studies is, you can do it with RTDS, but the price goes up based upon every time you add another 50 nodes. So what I'm seeing is the events on the system are driving us to really come up with innovative ways of working together, and I want to compliment the whole PNNL Advanced Distribution Managed project, where they really brought together the best of the researchers, the software developers, and do it. We just have to do a lot more of that. there's a tendency for us to get siloed. Well, people don't realize how competitive it is to get a PhD, isn't it? I mean, you've got to get your paper published before anybody else. Well, we kind of have to have a rising tide benefit everybody so that the researchers will really share and we get more cooperative papers written with multi-university, multi-vendor, multi-lab cooperation, okay? And you know, I want to thank, you know, Kevin and Ron, the whole PNNL team for making that happen, right? We just have to have a lot more projects like that. And you've seen the amount of stimulation, you know, that you get. So we're at a point right now where, yes, people are truly aware that we have to model these effects. I always use the Galloping-Gertie Bridge, all right? The Galloping-Gertie Bridge was built with trusses that were about 1/10 what they are now, okay? Well, when you open up the Pacific AC intertie, you are seriously weakening the whole system of the Western United States, all right? So it's a matter of communicating to everybody up and down the chain, managers and everybody about how doing really first-class modeling is really important. And unlike my son was a Marine Cobra pilot, the Marines spend $1 billion a year on simulation, okay, in order to train them. We don't have those budgets in our business, but so we got to make the best of what we have today.
So I don't see any hand raised here, so I'll kind of ask a concluding question. We have the Tobos coming online. Go ahead.
Well, I'll just follow up a little bit on what Robin said about all the new technologies coming online and how to model them. One aspect of that is that the number of items, the number of things you're modeling increases. So there is that question. The question of what phenomenon you have to actually model may be a little simpler for the OTS, because you see what we actually model in the OTS are things that the operator can see. So we don't usually model the fast phenomenon in detail. We only model enough of the fast phenomenon to find out what happens that the operator will see. So that's a little, I mean, you have some room to improvise instead of having to run, 100 racks of RTDS.
Yeah, I have a story on. You remember we had the OTS user group, and we actually went to the I think it was the American Airlines flight simulator facility in Dallas, and they had all these $20 million flight simulators, and the lead instructor there said, we always use the simplest approach to teach the learning objective. So if we can do it with a cardboard mock-up, we do it with a cardboard mock-up, okay? And so again, I use a Navy example is when you fly a T-34, you're in there with two pilots, and you literally roll the canopy back and stand up on your seat and jump out of the plane, okay, with a parachute. So down, and forgive this, but down south, they call it redneck parasailing. They tow you behind a pickup truck with your parachute until you go way up in the air, and then you have to cut loose and land. So there's a lot of, for training, you don't have to do everything. You can model a little piece of the system and get the principle across on you versus the real-time response. So yes, we have to do that. We have to get to the bottom of if what is it about this phase lock loop stuff and these inverter-based devices. How detailed do we have to really do the modeling, okay, to get those phenomena? And I don't know the answer. Someone out there needs to tell me, okay? So.
Great, thanks, Robin. So maybe just a parting thought. So what recommendation do you have for our students for working in the power area and maybe have entrepreneurial aspirations? What would you like to say to them?
Please, I have just send me an email, okay, with your background. A lot of you do have a really good LinkedIn page, and just email me about what whatever it is you're interested in that has stimulated your thinking from this particular presentation. Yeah.
Excellent. Thank you so much, Robin, for spending time with us today. We greatly appreciate your time and talk. And we'll definitely follow up with you and we'll share your information with our students, and hopefully you'll hear back from them if they have something to follow up. And this was very insightful and topic for us to, sorry, I got distracted with the chat a little bit. I thought there's a question, but thank you so much, Robin, for spending time with us, and have a great day. We'll call it a day today for the seminar.
Thank you all so much. Bye now.